This is the second video of a 3-part series detailing the vacuum infusion process. In this video, we will begin with a safety overview. Then we will demonstrate how to perform a vacuum infusion. Finally, we will showcase the effect of resin flow speed on part quality, and show ways to control the flow speed. The first part of this video will go step by step through a common way of setting up a vacuum infusion. The second part of this video will examine the effect of resin flow speed on porosity by observing infusions with slightly different setups. Proper safety measures must be followed when performing a vacuum infusion. The following safety equipment are often worn: gloves, lab coats, and safety glasses. Also, it is important for those with longer hair to tie their hair back. Please note that there are harmful chemicals, vapors, and materials used in this process. Before beginning the vacuum infusion, make sure to follow all safety protocols specified by the material manufacturers. Meet with local safety officials to make sure that all safety protocols are being followed. Vacuum infusions require one-sided, vacuum-tight tooling. The tool provides the shape of the part. In this case, we are making a flat panel, so we are using a flat tool. Tools are also known as moulds. Before placing the fiber bed onto the tool, a mould release is applied. Now, we will cut the glass fiber to shape using electric shears. Scissors or a rotary cutter are often used as well, and templates can be used to ensure the fiber is cut to the correct size. Place the fiber on the tool. To help it stay in place, we can use small pieces of tape on the edges of the part. On top of the fibers, we will place a peel-ply layer. This allows our vacuum bag to release from the part and creates a surface that is good for bonding. Peel-ply is permeable, and its presence will affect resin flow, so it's important to consider where and when it is used. We will place the vacuum outlet about 2 inches from the part. This will act as a resin break, preventing resin from entering the vacuum outlet. The location of the resin inlet can vary. Common practices include infusing the part from one side, placing the inlet in the middle, and placing inlets around the perimeter of the part. We often try to select the best option that will minimize the resin flow distance. For this part, we will place the inlet tube along one edge. Having the inlet tube directly in contact with the fibers allows the resin to flow unobstructed through the fiber matrix. Note that leaving the inlet placed on top of the part leaves an imprint. For larger parts, we can use multiple inlets that are opened sequentially. Once the flow front reaches the next inlet, that inlet is opened and fresh resin is allowed to flow. This is an example of the process used to make boat hulls. We will now place the vacuum bag onto our fibers. Ensure that there is enough bag to reach into all corners, otherwise the bag will bridge and race tracking will occur through the empty area. Pleats may be required to provide enough bag material, especially with parts that have lots of contours or geometry changes. After placing the vacuum port and bag, we will connect the vacuum system. We will use a catch pot to ensure resin does not enter the vacuum pump. After everything is connected, we will clamp off the resin inlet tube and perform a vacuum drop test. This is done by first pulling vacuum on the layup, then disconnecting the vacuum source and monitoring the vacuum level. The acceptable amount of vacuum drop depends on the size of the part. For our part, we will accept a drop of 5 inches of mercury over 30 minutes. Some drop may be a result of volatiles being evacuated from the fiber or tool, but if the vacuum drops an unacceptable amount, a leak is likely present and should be located and eliminated. To detect a leak, you can listen for a slight escaping of air, then go around the vacuum bag and ensure that there are no small air channels between the bag and the tacky tape. A higher quality vacuum on the layup is more likely to produce a higher quality part. Once the layup is confirmed to be acceptably vacuum tight, we will hold the part under vacuum for as long as possible. This removes as much entrapped volatiles as possible, reducing the chance of dry spots or porosity in the final part. Moderately heating up the layup can increase the effectiveness of this step. We will now prepare the resin. We can estimate the amount needed based on the fiber area and predicted fiber volume fraction, plus an additional amount to ensure the inlet tube stays submerged in the resin cup. We will keep the two resin components, the resin and the hardener, in two separate containers. These containers can be placed in the resin pot, and vacuum is pulled to degas the resin by removing any dissolved volatiles. After a period of time, they can be mixed together, then degassed again to remove any air bubbles introduced in the mixing process. Please refer to the KPC articles linked below for more information. After degassing, we will attach the resin cup to our laminate. Be sure to minimize the amount of air introduced into the layup when unclamping tubes. Once the resin is ready to be infused, a partial vacuum is pulled on the resin pot and the resin is injected. Initially, the resin quickly enters the inlet tubing and slows down as it enters the fiber. The flow speed of the resin decreases as the distance from the inlet increases. This follows Darcy's law, as discussed in the first video of this video series. It is important to observe the grid lines on the vacuum bag. These grid lines are used to gather position versus time, aka flow rate, data. This data can be used to calculate permeability and other parameters about the part. The data for this specific infusion is shown on screen. As the infusion progresses, the resin flow front stays uniform, and one can tell that the flow rate has slowed considerably. This is exactly what we want to happen in our infusions. There are no signs of race tracking or other defects. Moreover, this allows the part to have a good fiber volume fraction. Overall, this infusion went smoothly. When the resin has fully saturated the fiber, and preferably before it has made its way into the outlet line, the resin inlet can be clamped off. We usually leave the inlet tube in the cup of resin to reduce the chance of air being drawn into the part. We leave the vacuum pump running while the part is curing. We will now leave the part to cure under vacuum. The resin will continue flowing and equalizing any pressure gradients until it gels. The time before the resin gels depends on the temperature and how long a particular resin takes to gel, which can be found on the corresponding resin data sheet. After the part has fully cured, we will turn off the vacuum pumps and remove the consumables. We will also trim down some of the excess resin surrounding the part. A common initial test when inspecting glass fiber parts is to hold them up against a light source. The light can penetrate through the glass fiber and show some of the porosity in the part. As discussed in the previous video, the infusion parameters can drastically affect the part outcome. Here we have 3 identical panels with slight variations designed to demonstrate the effect of the resin infusion speed. The first panel on the screen has a ply of flow mesh on top of the fiber bed. The second panel on the screen has a heat pad underneath the tool, and the final on-screen panel is a standard infusion panel. In this sped-up view of the panels, we can see that resin travels rapidly through the panel with the flow mesh, fairly slowly in the control, and moderately in the heat-padded infusion. There is an ideal flow rate to reduce porosity. If an infusion's flow rate is too slow, then macro voids will become more common. If an infusion's flow rate is too fast, then micro voids will become more common. Using flow meshes, heated resin, clamped inlets, higher viscosity resin, less permeable materials, and more will all affect this ideal flow rate. Depending on the setup of the infusion, using a flow mesh might be the optimal way forward in terms of part quality, even though it speeds up the flow front so drastically. This is counterintuitive, as typically, using flow mesh will reduce the quality of the part by creating porosity. Although the infusion using flow mesh was the quickest, it did not produce the highest quality part. Generally, the faster the resin moves during impregnation, the higher the probability of porosity or other defects. The panel shown on screen demonstrates this phenomenon. On the left-hand side of the panel, the resin flowed very quickly through the first half of the part. Towards the second half of the part, the flow mesh ended and the resin flow slowed. As you can see, the left-hand side of the part is riddled with porosity, whereas the right-hand side of the part has almost no porosity. This relationship between resin flow speed and part quality is crucial to understanding the vacuum infusion process. Depending on one's application, each variation of the process may be used. For higher quality parts, an infusion using a clamped resin inlet may be ideal. For a faster production rate process, using the heat pad or flow mesh may be ideal. Trade-offs between part quality, production rate, and cost are at the heart of the decision of what vacuum infusion process to use.
Thanks for watching. To see more virtual labs and learn more about composite materials, make sure to subscribe to the CKN YouTube channel.